if we heat something but we don't change the temperature? When does that happen? It happens whenever we're changing state or phase. And that means going from a solid to a liquid, or a liquid to a gas, or in the other direction. Anytime we're changing state, temperature doesn't change because all of that energy goes into changing the bonds, either breaking them or rearranging them. Now we call that latent heat. Anytime we have a heat put in or taken out, but no temperature change, that is latent heat. Now there's actually six different heats that we need to look at. Now the first one is the hardest to remember because its name doesn't really tell you what's going on, and that's the molar heat of fusion. And this is the energy or heat absorbed when 1 mole melts at a constant temperature. Now anytime you see molar heat, and you'll see 6 of them, well, heat is just energy, and molar in this case is referring to 1 mole. So the energy of 1 mole, and fusion is melting. So the energy of melting 1 mole. So energy of melting 1 mole. That is the molar heat of fusion. Now on the opposite side is the molar heat of solidification. And this one's a little easier. This is the energy, that's heat. Solidification is, of course, going from a liquid to a solid. And molar, we're just saying 1 mole. Energy to solidify 1 mole. Now it turns out the energy to melt something is equal to the energy to solidify something. Of course, they're opposite directions. One is exothermic and one is endothermic, but they're the same. So if I want to melt 1 mole of ice, that takes the exact amount, opposite direction, to solidify or freeze 1 mole of the same substance. So they have the same value. So let's look at a problem here where we're looking at ice. And it says how many grams of ice will melt? Well, melting is our heat of fusion. Now if we look in our book, we can find the heat of fusion on page 521 at the very top of the page. They tell us our heat of fusion for ice is 6.01 kilojoules per mole. So 1 mole takes 6 kilojoules to melt a mole of ice. So of course 2 moles would take twice that, 12 kilojoules, and 3 moles would take 18 kilojoules. So that's how much energy I either have to put in to melt ice or I have to take out to freeze the ice. So let's look at this problem. I'm given a temperature, but again, in change of state or phase, temperature doesn't matter because temperature does not change. So cross off temperature. So I'm starting off with 2.25 kilojoules of heat. So I'm going to write my given. And like always, if I'm converting something and I don't want it, I put it down there to cancel it. Well, on top I can put moles. I'm just using this ratio right here. Of course it's inverted, it's flipped, but it's the same thing. And right here it says, well, it takes 6.01 kilojoules to melt 1 mole. I have 2.25 kilojoules, so I'm going to cross off my like units. I'm left with moles. Well, so I'm not done because the question says how many grams. So I got to keep going. Alright, since I don't want moles, I'll put it down there. And I do want grams. Well, grams to moles, we've done that a lot. That's molar mass. And this is ice, which of course is H2O. So I need to find the molar mass of H2O. So I go to my periodic table, I look up hydrogen. There's 2 of them. And I look up oxygen. And I add those together, and it's 18 grams per 1 mole. That's the molar mass. I'm going to cross off my like units. Now I'm done, because my question is asking for grams, and that's what I have. And so I would multiply and divide that out. Alright, 21 and 22 are similar, so you can do these on your own if you want, and I'll do them now. So on 21, let's see, we're starting off with 10 grams of popsicle, which we're just going to say is water, it's ice. And they want to know for 21 how many kilojoules are needed. Alright, so let's get out of grams. Let's get into moles. And again, for water, or for anything, it's 1 mole. And we're looking up on the periodic table, hydrogen, hydrogen, and oxygen, that's H2O. Add those together, and that's my molar mass again. Same thing as the last problem. I'm going to cross off my like units. Grams over grams goes away. So now I'm in moles, but the question doesn't ask for moles, so I'm going to keep going. And it does ask for kilojoules. And I do know my ratio of kilojoules to moles. That's at the top of page 521, and it says that it takes 6.01 kilojoules for 1 mole. Cross off my like units. I'm left with kilojoules. I multiply that all out. Alright, 22. Let's see, I'm given kilojoules. And the question is asking me how many grams can I melt with that. So again, I'm going to match my units. Whatever I start with goes on the bottom. I'm given the ratio of kilojoules to moles. That's at the top of page 521. And it tells me there that 1 mole is 6.01 kilojoules. That's given to me. Alright, cross off my ratio, or cross off my like units rather. Now I'm in moles, but the question says grams, so I'm not done. So if I don't want the moles, I'm going to put them on the bottom. And I do want the grams. And again, this is water, just like the previous problem. So grams to moles, I go to my periodic table and I add up the numbers from there. And I have 2 like units, moles and moles, so I'm going to cross those off. I'm finished. I have grams. The question asks for grams. And so that's my answer. Alright, so that was melting and freezing. Well, we can definitely go from another state, and we can vaporize something. So to vaporize, of course, is to go from a liquid to a gas or a vapor. And so the molar heat of that is the energy to vaporize 1 mole. That's the molar heat of vaporization. Now for water, that's much bigger, because now I'm breaking those bonds apart, and the water is completely leaving the other waters and turning into a gas. So for water, the molar heat of vaporization is 40 kilojoules. Oh, what if I want to go the other way? What if I want to change it from a gas to a liquid? Well, that's the molar heat of condensation. To condense something is to make it smaller. So if I have a gas and I want to shrink it down, turn it back into a liquid, I'm going to use the molar heat of condensation. Again, that's the energy required to condense 1 mole. And it turns out that the heat of vaporization is equal, but opposite, to the heat of condensation. So again, to vaporize something, for water anyways, it's 40 kilojoules per mole. And to then condense it, it is 40 kilojoules per mole. Now this is going to be exothermic, and this is going to be endothermic. So they have the same value, but in opposite directions. So in summation of these 4 heats, I have my 3 states of matter from a low energy to a high energy, solid, liquid, gas. And I see if I want to go from a solid to a liquid, if I want to go to a higher level of energy, I have to put energy in. So this is exothermic, it's positive. And if I want to go from liquid to a vapor, a higher energy, I have to put energy in, so that is vaporization. To go the opposite way, exothermic, I have to take energy out. Now sometimes this confuses people, because if I want to turn liquid to a vapor, I think, hey, I got to put it on the fire. And everybody knows fire is exothermic, it's hot. But we got to think about it from the water's perspective. If I'm water, and I want to get to steam, I have to get energy in. And that's why this is an endothermic reaction. All right? And if I want to, let's say I have some liquid water and I want to freeze it, well, what do I have to do? I have to take energy out. I have to remove energy, and so that's exothermic. This here is a heating curve. This kind of reinforces the idea that when we change state, temperature doesn't change. So here I have a constant heat supply, and here's my temperature. So this is for water. So here I have some very cold ice. As it heat is supplied, my ice warms up until it gets to right here. Well, this is the melting point. At the melting point, you see my temperature does not go up anymore. Now it's flat. And this is my fusion. So now the bonds are being broken, and so temperature is not increasing. Once it's all melted, now my temperature starts to increase again. My water gets hotter and hotter and hotter until the vaporization point, the boiling point. And again, another flat line, as all of the energy that is put in changes the state from a liquid to a gas. And you see the vaporization takes much longer than the fusion, because here we're just kind of jostling the molecules around. Here we're completely separating them. And once it is all vaporized, then I can heat up my vapor for pretty much as long as I want to. These are some values that are in your book. This table is in your book, and you see the heats of fusion, which of course are the same as heat of solidification because they're equal but opposite. And my heat of vaporization, which is equal to my heat of condensation, which again is equal and opposite. So anytime you need some values, you're going to look to this table. And then we have another heat, a heat of solution. Well, it turns out when I make a solution, heat is generally either released or absorbed, but there is a temperature change. If I have some sodium chloride, some salt, and I throw that into water, when it dissociates, when it breaks apart, there's actually heat released from that. Now, it's too small for us to feel, but it does happen. So pretty much any solution, when it's made, will either gain or release some amount of energy. And we, of course, call that the molar heat of solution, the energy involved with turning 1 mole into a solution. And to work out these problems, they're no different than the others. Here I'm making a solution of sodium hydroxide, so I'm going to start off by writing out the given. And I don't want the mole units, so I put it on the bottom. They tell me, oh, they don't tell me, but if I look on my book, this is on page 525, they tell me it is 445 kilojoules per mole. I cross that off, and so I'm in kilojoules, and that's my answer.